Welcome back. Second day of Riemann sums and definite integrals we're going to introduce today. Just a quick recap. We've been talking about techniques in finding area underneath the curve. So these first three examples that you see here, I can guess that you guys probably have an idea how to find area underneath these curves. You can use geometric shapes to find area underneath the curve. So the very first one is pretty easy. Pi r squared is the area of a circle. Well, it's a half a circle, so make sure you divide that by 2. The radius is 2 here, so you're going to have basically 4 pi over 2, which is 2 pi. There's your area for this one. I can go through a few of these. You can break these up into a lot of different shapes. If you really wanted to, you can try to count the squares, and then, but that won't always actually help you. But this first one you can do 1/2 base times height for the area. Then the last one, 2 techniques. You can use a trapezoidal rule. For that, you would have 1/2 times the height, base 1 plus base 2. Remember, the bases are the 2 parallel sides. So in this case, these would be the bases, and the height would actually be the distance between the bases, which would be 4. So to finish this one off, the height would be 4 here. Base 1 is 1. The other base is 2. Oops, I put in h for height. Sorry, there's 4. So technically, 1/2 times 4, which is 2, times 3. So I should have an answer of 6 here. So there's just a couple quick, hey, don't forget you know how to find area of shapes. Kind of moving back into what we talked about last time, we have Riemann sums, and we're going to try to connect this back to calculus. So far, we've been talking about finding area underneath curves using rectangles, but that has really seemingly no connection with calculus until today. So if we were to consider the function root x, which you see graphed here, just on the interval from 0 to 1, and you can see that it's kind of shaded underneath that. Well, what we've done is we've done subintervals and rectangles and added up these rectangles. If we did just say 2 rectangles here with right endpoints, just draw that quickly, that would be an over approximation, which wouldn't be as good. So you might say, okay, well, how can we make this a little bit better? And that's exactly what we're going to be doing today. We're going to find the best way to find this. So let's say we have 4 subintervals. Let's do right endpoints again. And you could still see, sorry, I didn't space these out exactly, but you can still see it's going to be an over approximation. But so that's with 4. So one more time. Let's maybe divide that in half again and do a bunch of these rectangles. And sorry, I'm going quick here to give you the idea, but you see how it's actually getting a little bit better. The over approximation, those little triangles that are kind of above the curve, are getting smaller and smaller and smaller the more rectangles you do. So the obvious question would be, well, how many rectangles would be the best? And that kind of gets into the connection with calculus. So we are going to be doing a lot of rectangles, and it would suck to have to find the area of 100 rectangles. So we're going to kind of bring this back and connect it into other things that we've talked about in calculus. So before we get too far ahead of ourselves, I think this lesson is really important to understand what is this. And it's really, really basic. It is sigma notation. So first off, sigma, this right here, is basically means the sum. So you're going to be adding up a bunch of things. So you start at 1 and you go to n at the top. And what that actually means is, what if we had 1 rectangle? Or what if we had 2 rectangles, 3? And you're going to keep counting all the way up to n, whatever n is. And this piece here, you guys are extremely familiar with, even though it looks really ugly. This f of c, well, that's like f of x. So when you plug an x value in to a function, you get the y. So this is really the y value. And delta x, so we have change of color. So if we have these 2 x's here, bad color. this distance is delta x. Well, that's like the width of your rectangle. So really that's like an x value that stands for the width. So now we have base, width and base are the same thing. The f of c is like your height, that's the y value, times the width. So that is area of a rectangle. So this box that I've drawn in red, that is actually finding the height times the width. That's the area of a rectangle. And that sigma in front of it is saying add up a bunch of those. And how many? Well, n is really what it's saying. So that's what that notation really means. So connecting this back to calculus, remember how many rectangles would make this the most accurate? Well, a million, or billions of them. And it would actually be, the more and more rectangles you have, the smaller these little over approximations will be. And eventually, if you get, so many, an infinite amount of these rectangles, the area will be so small that the area underneath the curve will be exact to so many decimal places. And we only need to be accurate to 3. So this at the end is the big important piece. This is saying that sigma notation that we just talked about up there, if you take n and have it approach infinity, meaning an infinite amount of rectangles, and add up the area of them, you will find area under the curve. Exactly. And some might say, oh, well, how exact is it going to be? Well, you could be exact to a million decimal places, and we only care about 3. So really, it's good enough for us. So you probably heard your physics teacher say that a few more than once. So you may or may not have this in your notes packet, but I thought this was a nice little kind of transition. So what we just talked about here, this ugly notation that we just did, that is actually doing an infinite amount of rectangles. So what does that mean in calculus? Well, instead of writing all this limit of the sigma notation, all that, we have this very nice integral over here. And for the first time in this class, it has a and b. These are called the upper limit of integration and the lower limit of integration. Basically, it's your interval, your starting and your stopping point of the interval. One small note to say here is, instead of saying let n approach infinity, which is like the number of subintervals, another way of saying is that delta x again is the change in x, so change in here. So if you had an x value here, another x value here, that ends up being the width, right, of the rectangle. Well, if that's approaching 0, that means that those two x's are so close together that the distance between them is actually approaching 0. So if you had a width of almost 0, there's going to be an infinite amount of rectangles. So that's just explaining that. How important is that for you? I wouldn't say it's too essential to know, but that's explaining this. So we have now introduced this definite integral and how all this actually connects back to calculus. So what you may see in your notes is this. And this is very similar to what I just said, but it has a lot of technical math syntax, so it's worth a read through. But since I use those other 2 examples, we can kind of skip ahead through this. The main thing is that this is called a definite integral, and this finds area underneath a curve on any interval exactly, not approximating. It'll tell you the exact area under the curve. So what we can do now is kind of transition back. Knowing this notation now, we can actually find area underneath all these curves exactly. And how we're going to do that is drawing a picture, and we're going to use our geometry skills. So this should be super easy, kind of almost fun to do. So pictures are nice to do here. Mine are going to be very rough sketches, but we are going to graph the function, and actually the function in this case is just 3. You can think of that as y equals 3. 1, 2, 3. It's a horizontal line, right? So let's say that's y equals 3. And we're finding the area under the curve. Remember, that's what the integral means. But I'm doing it from 2 to 9. So if you're just trying to draw these vertical lines here, the area underneath this curve is a nice geometric shape. It's a rectangle. So its height is 3, and its width, or base if you want to call it that, is 7. So area underneath this curve is exactly 21, just using our algebra skills, or sorry, geometry skills. So second one, B here, is interesting. Not many of us, oh, I'm sorry, I thought it was something else. This is just the absolute value function. So got this nice V shape, and we're doing this from -2 to 1. So we're finding area underneath this curve. And actually, if you think about this, this is kind of nice. It's in 2 pieces. So we've got this piece here and this piece here. So I might do 1/2 base times height. The base on this one's kind of easy. That's 2. The height, okay, well, if you're paying attention, you plug in the x value of -2. That would be the y value right here. -2 absolute value, that is 2. So that's going to get you the area for this one. And over here, 1/2 base would be a distance of 1. The height would also be a distance of 1. So we've got 1/2 over here and 2 over here. This is going to be 2.5. Okay. All right. And this is a very famous problem. You see this quite a bit. Just without a calculator. These would be done all without a calculator, by the way. Without a calculator, you need to know what that graph looks like. And, you know, we stumble over this problem every year, and you need to see it like once or twice, and hopefully this one won't fool you anymore. But this equation actually comes from this. X squared plus y squared equals r squared. That's the equation for a circle. And if you go ahead and solve this for y squared equals r squared minus x squared. So y would be plus or minus is important here. R squared minus x squared. R obviously being the radius. So in this problem, r would be 3. And notice I have a plus or minus here. That's because that's the top half and the bottom half of the circle. Well, the sign we have out front here is positive. So it is only the top half of the circle with a radius of 3. So you can kind of count that. And poorly drawn circle there, half circle there. So we just need to find the area underneath this guy, which I believe is what we did in our introduction problem. So pi r squared over 2 with a radius of 2, you're going to have 9 pi over 2. All right, so that is understanding that the definite integral is finding area under the curve exactly, and we're going back to using our geometric rules and area formulas to be able to find exact area underneath there. All right, so here we got a new problem. We're going to sketch a graph of this. Don't forget your Algebra 1 skills here. This is a line with a y-intercept of 3 and a slope of -1. So I don't know if I can draw a straight line here, but I will try. Okay, and we are finding the area underneath here from 4 to 8. Okay, so this area actually forms this shape, and an important note to have here that this area is below the x-axis, so this is going to be a negative area. Any area that's below the x-axis is going to be negative. There are actually 2 ways of doing this. You could actually section it off and do a rectangle and a triangle there, or you might want to just do a trapezoid. So just because I know we're not too comfortable with the trapezoid, I'm going to do the trapezoid. So it's 1/2 times the height, and then base 1 plus base 2. So height, again, is distance between the bases, so it's actually this, so that's 4. And then base 1, I'm guessing is 2. Now, how could I know for sure? Well, if you take the x value of 4 and plug it into the equation here, am I wrong? No, I am wrong, sorry. Yeah, if you take 4 and plug it in, good thing I checked, you would get 3 minus 4, which is -1. So we have the -1 there. And then it goes to 8, so I might take 8, plug it in there, and I would get -3. Wow, -5, let's say. Sorry about that. All right, and to finish this off, you get 2 and -6. Definitely going to get you -12, and it makes sense that our area is negative because this is below the x-axis. So I'll go kind of quick through this next piece. These are integration properties. So interesting things I'll talk about quickly. If you integrate from A to B, that's kind of going forward in my mind. Well, if you integrate from B to A, that's kind of integrating backwards. Well, that's the same thing. If you put a negative out front, you can switch it. So for example, if you're integrating, say, from 2 to 1, in my mind, that's backwards. Well, what you could do is take out a negative and switch that so that you're kind of integrating forwards. Kind of a useful rule if you're kind of, and if you don't like working backwards, you know, kind of simplifies things a little bit for you. Number 2 actually is kind of logical. If you start at A and end at A, you didn't really go anywhere, so there's no area under the curve. It would be like a line, and a line has no width, so area under the curve, if you start and stop at the same place, 0. We've used this one quite a bit. If you have a coefficient, you could take it out front. If you have a sum, you can break it up into 2 integrals. And here, this is you gotta pay attention to the limits. If you start at A and go to B, and you add, same function by the way, then you go from B to C. Well, let's do A, B, C. Well, if you take, C looks like that. If you take A to B, and you add B to C, well, that's the same thing as going from A to C. That's what that last one is. Okay, so quickly kind of looking at a couple of these. I might not do all these for you. So these are always good problems because some people look at this and like, well, what's the equation? I can't do it. There's just f of x's and g of x's. I don't know what they are. Well, it's like geometry. They'll have a couple givens. So, for the first one, you've got f of x and g of x with a sum. Remember, you can separate that up into 2. F of x from 2 to 6 is 10. G of x from 2 to 6 is -2. So that would be 8. All right. Same thing with the subtraction, just another way of doing that. Remember, 3 can come out as a coefficient. So really, it's just 3 times the integration of f of x from 2 to 6, which is 10. And yeah, that looks good. So let's see if I can find a nice one out here. This one only has one thing. Just tells you that the integration of sine of x from 0 to pi is 2. Holy cow. I don't know if you guys can hear that, but my 2-year-old and my wife are having fun at bath time right now. All right, so back to this. Couple interesting ones. So let's see if I can find. Oh, yeah, this one is a little bit interesting. So you have to go back to the sine curve. Remember, the sine curve looks like this, right? That's one period of it. So you have to remember, it also goes the other way. So that's 0, that's pi, and that's 2 pi. So if you integrate from 0 to 2 pi, well, you have a positive area here and a negative area here, and they're exactly opposites. That's going to be 0. And if you integrate from pi to 2 pi, like A, well, that is going to be negative, and you know that the first half is 2, so the other half should be -2. And you can kind of go on from here, so for C, from 0 to pi over 2, well, that's half of this, so you could say that that's 1. If you work the other way, from negative pi to pi, well, those can be completely cancel again, so that's 0. All right, and then finally, E. E is interesting. Remember, this is a sum, so you can separate this, and you really should. So one part of it, the second part of it's easy. That's the given. So I know that this answer is going to be 2. But this is not just 2. This, imagine if you'd integrated this algebraically. This would be 2x. Actually, before I teach it that way, how about this? Let's look at this one graphically, because we did this today. This is the line, y equals 2. If you integrate that from 0 to pi, well, now you have a rectangle whose height is 2 and whose width is pi. So base times height, 2 pi. Final answer. Okay, so the next thing, you have a couple of practice problems that you guys can work on yourselves. So I hope you learned a little bit here. Remember, you can always pause this if I move too fast, or you can watch